Good morning all of you. My name is Ashutosh. I'm a teacher by profession. My mission is to impart quality education to all. For that purpose I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture we'll try to discuss some of the questions that has previously been asked in GRATE examination. So before we solve different questions, let us discuss few important points. We had already discussed that Routh Hurwitz criteria is an extension to polynomial theory which basically helps us to check whether the given system is absolutely stable or not without solving the complete polynomial. It does not give any information about the relative stability of the system. With the help of Routh criteria, we could only specify that whether a given system will be absolutely stable or unstable system. We already know that positive real part of poles makes our system unstable. Basically, if any system possesses poles with positive real parts, then the response of that system will become unbounded, which makes our system unstable. So with the help of Routh criteria, we can find the number of poles which possess positive real parts, which actually equals to the number of sign changes in the first column of Routh array. We have already studied that. Transfer function of any system will be given as it is the ratio of output to the input CS upon RS, that is equivalent to GS over 1 plus GS HS. Here GS is the open loop transfer function. So in order to characterize the stability of any system, we are only concerned about this characteristic equation of the system. But same polynomial theory will also be applicable for the positioning of zeros, as they will be the roots of the numerator polynomial of the transfer function. If we have to characterize the positions of zeros, we could also characterize the positions of zeros with the help of same Routh criteria by forming the table of numerator polynomial and checking out the number of sign changes. So number of sign changes in the numerator polynomial of the Routh array will gives us the position of zeros, or the information about the number of zeros which actually possess positive real part and negative real part. While solving the problems, one should be very careful about the given data, that whether the open loop transfer function is given or a closed loop transfer function is given, and we have to solve that question accordingly. So now we're going to take up the questions. So in our first question, it has been given that a system described by a transfer function g of s is equal to 1 over s cube plus alpha s square plus ks plus 3 is stable. The constraint on alpha and k are, a stable system is being given and we have to find the conditions over alpha and k. So without wasting any time, let us create the Routh table for the given transfer function. One point should be very important to mention here is the transfer function is being given, but it hasn't mentioned any negative unity feedback system. So we just continue our calculation while considering the transfer function of any given system, whose denominator polynomial will going to gives us the information about the stability of the system. So let us quickly create the Routh table for the given transfer function. So characteristic equation being given as s cube plus alpha s square plus ks plus 3. So Routh table for the given polynomial will be given as s cube and s square. We have to write down the coefficients of s cube is 1, then after skipping next coefficient we'll be having k, then the coefficient of s square is alpha, and then skipping another coefficient we'll be having so s alpha times k minus 3 divided by alpha, and then next column will be 0. So again s to the power 0, what will be the Routh table? Alpha k minus 3 times of alpha into 3 minus 0 divided by same this coefficient. We are left with 3 and next coefficient is 0. So we have provided the information that this system is a stable one, and for the stability of this system, the complete first row of Routh table should not gone through any sign change. For that thing, all these elements should be positive, as 1 and 3 are positive quantities. So this gives us the condition that alpha should be greater than 0 and the value of alpha k minus 3 should also be. It means alpha k should be greater than 3, which has been given in option number B. Hence this is your correct option. So now take another question which has been asked in GATE 2014. The forward path transfer function of a unity negative feedback system is being given as g of s is equal to k upon s plus 2 into s minus 1. The value of k, which will place both the poles of the closed loop system at the same location, is. So here open loop transfer function is being given and we have to count out the closed loop transfer function. So what will the value of closed loop transfer function? So closed loop transfer function is being given as 1 plus g of s is equal to 0. So we are left with 1 plus k times of s plus 2 s minus 1 is equal to 0. It implies s plus 2 times of s minus 1 plus k will be equal to 0. It means s square minus s plus 2s minus 2 plus k is equal to 0. It implies s square plus s plus k minus 2 will be equal to 0. If we closely observe this particular equation, this is second order polynomial equation in S. So with the help of Shridracharya, we can easily evaluate the roots of this particular given equation. So roots of this particular equation will be given by minus b plus minus under root of b square minus 4ac upon 2a equal to minus 1 plus minus under root of b square minus 4 times of a into k minus 2 upon 2. So if we want that both the roots of this equation will lie on the same location, then for that purpose the determinant, it means the value of capital D, this one, it should be equal to 0. So in what condition the value of this determinant will be equivalent to 0? Will be 1 minus 4 times of k minus 2 will be equal to 0. It means 4 times of k minus 2 will be equal to 1. It implies k is equal to 1 by 4 plus 2. It implies 4 to the 8 plus 1, which gives us the value 9 by 4. So the value of k for which both the poles of the closed loop systems lie at the same location will be k is equal to 9 by 4. This will be the final answer. So now let us take another question. It has been asked in GATE 2012. The feedback system shown below oscillates at 2 radian per second. This is your unity negative feedback system whose open loop transfer function is being given as k times of s plus 1 over s cube plus as square plus 2s plus 1, and we have to find out the values of k and a. So let us quickly evaluate the closed loop transfer function of the given system. Closed loop transfer function will be given as 1 plus g of s is equal to 0, which means 1 plus k times of s plus 1 divided by s cube plus as square plus 2s plus 1, means we are left with s cube plus as square plus 2s plus 1 plus ks plus k will be equal to 0, which could be rewritten as s cube plus as square plus s times of k plus 2 plus k plus 1. So now this is the characteristic equation of the given system. So now we have to evaluate the Hurwitz table for this. So let us quickly calculate the Routh table for the given system. S cube s square So the coefficient of s cube is 1. Then after skipping a, we'll be having k plus 2, and the coefficient of s square is a. Then after skipping this k plus 2, we'll be having k plus 1. So what will the value of next Routh array? A times of k plus 2 minus k plus 1 divided by a, and then 0. So now the next value is this whole a times of k plus 2 minus k plus 1 upon a will get multiplied with k plus 1, and then a 0 divided by this whole term. So we are left with k plus 1. So this is the complete Routh table. One important point should get clear in your mind, that frequency of oscillation is being given, that is equal to 2 radian per second, and frequency of oscillation will only existent when we'll be having a rows of zeros, or complete row is 0, so which generally occurs in odd powers of s. So this cannot be occur in this s cube, as this first term is 1. So anyhow it must have to occur next odd power of s, that is it should occur in this particular row. So this has to be 0. So this gives us a times of k plus 2 minus k plus 1 is equal to 0. This gives us a is equal to k plus 1 divided by k plus 2. So this gives us first condition in a and k. So now to calculate the values of a and k separately, we need two equations. So where do we will going to get the second equation? So frequency of oscillation is being given as 2 radian per second, and this is your ROZ, rows of zeros. So we're going to take up the auxiliary equation. So auxiliary equation is just above the equation of ROZ. So auxiliary equation could be written as a times of s square plus k plus 1 is equal to 0. So frequency of oscillation is being given as 2 radian per second. So now after putting the value of s is equal to plus minus 2j, we're going to have a times of 2j ka square plus k plus 1 is equal to 0. So we are left with minus 4 times of a plus k plus 1 is equal to 0. So this gives us the value of a is equal to k plus 1 by 4. So now comparing these two equations, equation number 1 and equation number 2, we can simply write down that k plus 1 upon k plus 2 will be equal to k plus 1 upon 4. This means k plus 2 is equal to 4. So this gives us k is equal to 2. So now again putting the value of k in this equation number 1, we have a is equal to 2 plus 1, that is equal to 3 by 2 plus 2 4, which is equal to 0.75. So option A matches, hence option A is correct. So now let us take another question, fourth question, which has been asked in GATE 2014. Consider a transfer function gp of s is equal to ps square plus 3ps minus 2 divided by 6s square plus 3 plus p times of s plus 2 minus p, with p is a positive parameter. The maximum value of p for which the given system will remain stable is. So we have to find out the maximum value of p for which the given system will remain stable. So again, it hasn't been mentioned here that the system is negative feedback, unity feedback or something. So we'll consider that gp of s as a transfer function of the system, and for evaluating the stability of the system, the characteristic equation will be the denominator part of the transfer function. I mean 6s square plus 3 plus p times of s plus 2 minus p will be our characteristic equation. So let us quickly calculate the Routh table of the given system. So Routh table for the given system will be calculated as s square. S, the coefficient of s square is 6, then after skipping the next coefficient 3 plus p, we will be having 2 minus p. Then the coefficient of s is 3 plus p and then 0. So the coefficient of s to the power 0 is 3 plus p times of 2 minus p minus 6 times of 0 divided by this 3 plus p. So we are left with 2 minus p, then again 0. For the stability of the system, the first table of Routh array should not gone through any sign change. So as we already seen, the first element of the Routh array is plus 6. So anyhow 3 plus and 2 minus p, both of them should be a positive quantity. So the first condition is 3 plus p greater than 0, and your second condition is 2 minus p should also be greater than 0. So first condition gives us p should be greater than minus 3, and your second condition gives us p should be less than 2. So here we'll be getting a range of p which will makes our system stable. So I mean p should be greater than minus 3 and it should be less than 2. So this is the range of p which makes our system stable. But question says that p is a positive parameter. So I mean the value of p should be positive. So it should be greater than 0. So again the next range turns out to be the value of p should lie between 0 and 2. So this is actually the range of p, but we have to calculate the maximum value of p for which our given system will remain stable. So maximum value of p should be just less than 2. So any value less than 2 will be the appropriate choice which makes our system stable. I mean if we going to take the value of 1.9999, that will make our system stable. So what if we're going to take the value at p is equal to 2? So at p is equal to 2, if we're going to put the value p is equal to 2 in this particular equation, we are left with 0. So this will become the row of zeros. But one should understand that rows of zeros should occur in the odd power of s, but it is your even power of s, so it shouldn't have any significance. So here we could consider that the maximum value of p which makes our system stable is p is equal to 2, which is your final answer. So now let us take another question. This is your fifth question which has been asked in GATE 2016. The transfer function of an LTI system is being given as h of s is equal to 2 times of s to the power 4 minus 5s cube plus 5s minus 2. The number of zeros in the right half of the s plane is. This question is little bit tricky. Please understand that in this particular question it is asking about number of zeros in the right half of the s plane. We had already mentioned that if transfer function is known to you, then the roots of denominator polynomial gives us the positioning of poles, whereas the roots of the numerator polynomial will gives us the position of zeros. So we're going to apply same Routh criteria in the given question. Since transfer function is being given as it is the ratio of output upon input, which could be written as 2 times of s to the power 4 minus 5s cube plus 5s minus 2 divided by 1. Since here we need to find out the number of zeros in the right half of the s plane, so we have to focus on this numerator polynomial in s. So let us quickly calculate the Routh table for the numerator polynomial. So Routh table for the numerator polynomial being calculated as s to the power 4 and s to the power 3. So the coefficient of s to the power 4 is 2. Then after skipping next coefficient s cube, please consider that here the coefficient of s square is missing, so we could write it as 0. So then again the coefficient is -2. So now the coefficient of s cube is -5, and then after skipping 0 we'll be having +5 and then 0. So how are we going to calculate the next row of Routh table? -5 times of 0 minus 5 to the 10 divided by -5, that turns out to be 2. Then -5 times of -2, that is your 10, minus 2 times of 0 divided by -5, that turns out to be -2. Again next coefficient is 0. So then next row is 2 5 is 10 minus 10, that is equal to 0, and then again next row is 0. So this actually becomes the row of zeros. So we need to evaluate the auxiliary equation and then complete our Routh table. So auxiliary equation turns out to be 2 times of s square minus 2 is equal to 0. So after differentiating this auxiliary equation, we have 4 times of s minus 0. So now putting the value of these coefficients, so after excluding this 0 and replacing with 4 and then 0, we have s to the power 0 is 4 times of -2 minus 8 minus 0 divided by 4, that is equal to -2. So now we have to calculate the number of sign changes in order to find out the number of zeros lies in the right side of the S-plane. So +2 to -5, one sign change. Then -5 to +2, this is your second sign change. Then 2 to 4, there is no sign change. Then again 4 to -2, there is third sign change. So there is actually 3 number of sign changes, which gives us the information that there are 3 number of zeros that lies on the right side of the S-plane, or which have positive real parts. Thank you very much for your patient hearing.